Alright, so today we are going to talk about continuity. Now, you have talked about continuity before. Remember, continuity is a continuous line, right? You can trace the graph without picking up your pencil. That means that that graph is continuous, it has continuity. We can also use limits to decide whether or not a function is continuous or has continuity at a specific x value. And the way we test that is by using this little, I guess, rule or theorem. But if we find the limit as x approaches some number, right, a, anything, of my function, f of x, once I find that limit by substitution or using a graph or whatever it is, it has to equal f of a, so plugging the number into the function. At first, we're going to look at using a graph to determine this, and then we'll look at substitution and some other things here. But this is the rule for deciding whether or not something is continuous or has continuity. So let's look at our first few examples here. Again, it's all going to, 1 through 12 here is going to come from this graph. So we'll start by finding the limit as x approaches 2 of f of x. So again, here's that theorem. Limit as x approaches a, f of x has to equal f of a. So I look at my graph. Here is x equals 2. So the limit as x approaches 2 of f of x equals 2, right? And f of 2, right? So when x equals 2, the y value is 2. Now, since these two things are equal, the question number 3 here is f continuous at x equals 2. We would say yes, because the limit as x approaches 2 and f of 2 are the same thing. Now let's look at an example when it's not going to be continuous. Now I know you can see on the graph that it's not continuous, but that's to kind of give you a visual of what we're going to use when we just do the substitution part, because you're not going to have that visual. But looking at number 4 here, the limit as x approaches 1 of f of x. Here's x equals 1. Here's part of the graph, and here's part of the graph. Since those things are at different points, there's that break, right? There is no limit as x approaches 1. So this limit does not exist. The value of f of 1 would be the closed dot, right? That would equal negative 1. Now, since these two things are not the same, f is not continuous at x equals 1. So we would say, no, it is not continuous. Looking at negative 2, again, I know you can see it's not continuous, but since there's this break at x equals negative 2, the limit as x approaches negative 2, again, does not exist. F of negative 2, again, would be the closed dot, so that would equal 1. And again, since they're not equal to each other, f is not continuous at negative 2. So we would say no. Number 10, the limit as x approaches negative 1. So here's negative 1. The limit as x approaches negative 1 would be negative 2. F of negative 1, so when x is negative 1, y is negative 2. And since those two things equal each other, f is continuous at negative 1. Okay? So again, if the limit is the same as plugging in that x value to the function, then it's continuous. If the limit and the value after you plug in are different, it's not continuous. So a lot of times we want to know continuity of piecewise functions, right? We want to know, are they connected or do they jump? So with a problem like this, the easiest way to kind of start the setup is to figure out, well, what's on the left side of 1 and what's on the right side. So we're just going to draw a little number line here, and that's x equals 1. So if I look at the top piece of my piecewise function, x squared plus 1, that's when x is greater than or equal to 1. So that means that's going to be to the right of 1. X minus 4 is when x is less than 1, so that's to the left. So here's where x minus 4 is. So 13. the limit as x approaches 1 to the right, right? That's what that little plus means. So here would be 1 to the right. So that means I'm going to use substitution and plug in 1 into x squared plus 1. And that would just give me 2. Now, the limit as x approaches 1 from the left, so this would be 1 to the left, right, the little negative. That means I'm going to plug in 1 to the bottom function, x minus 4. So 1 minus 4, which would give me negative 3. So, does the limit as x approach 1 of f of x exist? Since it's approaching different values on either side of 1, that means that it's going to be a jump. Right? On the right side, if you think about what that graph means, so here's 1. From the right, it's going to be approaching 2, so that'll be up here. From the left side, it's approaching negative 3, so that means it's down here somewhere. Okay, since those values differ, that means my limit does not exist. Remember, if they do equal each other, then the limit would be that value, and we would be good to go. But since they're different numbers on each side, limit doesn't exist. Now, f of 1 means we would plug into the top because of the greater than or equal to. So that would be 2. And again, since f of 1 and the limit as x approaches 1 are not the same, this is not continuous. Okay? So let's look at the next one. It gets a little bit more difficult here. Again, start by setting up your number line. This time I'm looking at x equals negative 2 and x equals 3. So the top equation, 2x plus 3, is on the left side of negative 2. In between negative 2 and 3 is x plus 1. And then the right side of 3 be 8 minus x. So the limit as x approaches negative 2 from the right. Okay, so that means I'm plugging negative 2 into x plus 1. So negative 2 plus 1 would give me negative 1. The limit as x approaches negative 2 from the left would be plugging into 2x plus 3. So 2 times negative 2 would be negative 4, plus 3 would be negative 1. So the limit as x approaches negative 2. Since these two are the same, that means that the limit as x approaches negative 2 of f of x does exist, and it is negative 1. Now, to figure out if it's continuous, I need to plug negative 2 into f. Now, this problem's kind of got a little trap in it. If you look at our domains here, there is no or equal to around the negative 2. So that means that there is no value when I plug negative 2 in. So since the limit as x approaches negative 2 and f of negative 2 are not the same, that means that it is not continuous. All right, now let's look around 3. So the limit as x approaches 3 from the right. So I'm plugging 3 into 8 minus x. So 8 minus 3 would give me 5. The limit as x approaches 3 from the left, so I'm plugging into x plus 1. So 3 plus 1 would give me 4. Now, since the right side of 3 and the left side of 3 are not the same, that means the limit does not exist at x equals 3. Plugging in 3, I'm going to plug into the bottom equation because the domain states its x is greater than or equal to 3. So 8 minus 3 gives me 5 again. But again, since the limit as x approaches 3 doesn't exist, and f of 3 equals 5, they're not the same, it is not continuous at x equals 3. Okay. Now we're going to get into some more, I guess, theoretical type questions. Okay, we have to remember our theorem here, limit as x approaches a of f of x equals f of a. right? That's my rule for continuity. Okay, so it says if f of x equals x squared minus x divided by 2x when x doesn't equal 0, and k when x equals 0, and it's saying that f is continuous at x equals 0, that means that I can use this rule. Then k equals what? So I need to figure out what k equals. So I'm going to use my rule for continuity to figure out what k is. So what I'm trying to do here, the limit as x approaches 0 of f of x needs to equal f of 0. So f of x is x squared minus x divided by 2x. And f of 0, so when x equals 0, that's the bottom part, right? So that's going to equal k. Now, if I think about doing limits by substitution, I have a fraction here, so I want to check the denominator first. So if I go right into plugging in 0, that's going to make that denominator 0, and I can't have that. So again, we want to start by thinking about factoring or rationalizing or simplifying the complex fraction. In this case, we have x squared, so I want to think about factoring that numerator. And I notice that I can take out an x. Okay, so the x's would cancel. I would have the limit as x approaches 0, x minus 1 all over 2. That's going to equal k. Now I can plug in 0. So I'd have 0 minus 1 all over 2 equals k. So that means k equals negative 1/2. All right. Let's look at another one of those. Now, this one's a lot more tricky because it's a multiple choice question. And we need to check when x is 1, and we need to check when x is 2. So, first thing I'm going to check is the limit as x approaches 1 of that big equation there. So 3x, x minus 1, all over x squared minus 3x plus 2. That 1 didn't show up. There should be a 1 there. So checking the denominator, plugging in 1, I get 1 squared, which is 1. Negative 3 times 1, which is negative 3. So 1 minus 3 would be negative 2, plus 2 is 0. So we got a factor. On the bottom, I need factors of 2 that add up to negative 3, so that would be negative 2 and negative 1. The x minus 1's cancel. Two. Now I can substitute. So plugging in the 1, I would get 3 on top. And then 1 minus 2 would be negative 1 on the bottom. So this would equal negative 3. So that's the limit as x approaches 1 of the top equation. Now I want to see what happens when I just find f of 1. So when I look at my whole piecewise function, when x is 1, my answer is going to be negative 3. So since the limit equals negative 3 and f of 1 equals negative 3, so I'll go ahead and write that out just so you can see it. If you don't want to write this out, you don't have to. But just to kind of show you the format here. So the limit as x approaches 1 of f of x is the same as f of 1. So we're continuous at x equals 1. All right. Now we got to check the same thing for x equals 2. We can go ahead and eliminate some answers here, though. Right? It's asking f of x is continuous except at x equals 1. Well, we just saw that it is continuous at x equals 1, so it wouldn't be A. We don't know anything about 2 yet. C, except at x equals 1 or 2. Well, we know 1 works. Except at x equals 0, 1, and 2, but we know 1 works, so it can't be that. At each real number, well, we haven't tested 2 yet, so we're going to have to test 2 now. Same exact process, okay? Now, I'm going to go ahead and skip all the factoring stuff because we already did that, and I'm just going to take my simplified function and use that. That'll kind of speed up the process here. So the limit as x approaches 2 of 3x, x minus 2. Now, there's nothing else I can do to simplify this function. So when I go to substitute and I plug in, the denominator is 0, right? But I can't factor anything. I can't rationalize anything. I can't separate a LCD out of that thing and simplify a complex fraction. There's nothing I can do. Now, when that happens, right, we would get something like that, but we can't have 0 in the bottom. If there's nothing you can do to that fraction, then we say that this does not exist. Okay? Now, plugging in f of 2, when x equals 2, my answer has to be 4. Now again, since these two things are not the same, we would say it is not continuous at x equals 2. So it's not going to be each real number, right, because it doesn't work at 2. So it's just b. F of x is continuous except at x equals 2. Okay? Now this problem is similar to that k-type problem. So it's asking, find the value of k so that f of x equals that mess is continuous at x equals 1. So we want continuity. So since this is a piecewise function, I need the limit as x approaches 1 from the right side of f of x to equal the limit as x approaches 1 from the left side. Right? Remember with piecewise functions, in order for the limit to exist, it has to meet each other. So that means the limit from the right side has to be the same as the limit from the left side, so that they're going to the same value. Now, we just got to figure out which equation's on the right side, which equation's on the left side. So, number line, here's 1. Looking at the domain here, x is less than 1 as the top equation, so it's the left side. So we have kx plus 1 on the left, and then x squared on the right. So we're finding the limit as x approaches 1 from the right of x squared, and we need it to equal the limit as x approaches 1 from the left side of kx plus 1. So substitute. Plugging in the 1 squared, k times 1 plus 1. Subtract the 1 over. So here k is going to equal 0. So if k is 0, that's going to make that thing continuous at x equals 1. Okay. Last problem. Same type of thing here. Okay. So find the value of p so that f of x is continuous at x equals negative 1. So again, I need the right side of negative 1 to equal the limit as x approaches the left side of negative 1. Number line. Negative 1. X is less than negative 1 is the left side, so x squared plus 2 on the left, x minus p on the right. So the limit as x approaches negative 1 from the right of x minus p has to equal the limit as x approaches negative 1 from the left of x squared plus 2. Substitute. Plug in negative 1 for x. So negative 1 minus p equals negative 1 squared plus 2. So negative 1 minus p equals 1 plus 2. So add the 1 over. 1 plus 2 is 3 already, so that would be negative p equals 4. Multiply by negative 1 on both sides, we get p equals negative 4. So when p is negative 4, if I were to put that into here, that's going to make that function continuous at x equals negative 1. And that's it. That's continuity.